Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're continuing with our series on writing a ray tracer in C++ using as far as possible only the standard libraries and the SDL2 library so that we can display results in a window. Now, it's been a little while since I've made a proper video for this series. I did the Christmas special and then I did a video announcing what was coming up in 2023. So if you remember what we looked at in the last proper episode of the series, we were looking at UV projection. What I want to talk about today is two topics that really on their own are not terribly exciting, but they are of fundamental importance to ray tracing in terms of, firstly, performance, and secondly, in terms of being able to better model or more easily model more complicated shapes. And these two things are bounding boxes and composite shapes. So we're going to look at both of those today, which hopefully will be of interest. So just quickly, as I always do before I get into that, I'll just say that if you like this video, please do remember to hit that like button, and if you haven't subscribed to my channel already, then please consider doing so that you don't have to miss any future videos. Thank you very much. Right, well, without much further ado, let's jump into it and let's have a look at bounding boxes and composite shapes. So if we consider bounding boxes first, a bounding box is basically, literally, what the name implies. It is a box that goes around any other shape or object that we might have in our scene, and its purpose is to prevent us having to test for intersections with that particular object or group of objects for every single ray that we cast into our scene. Now, bounding of boxes we've already touched upon when we looked at ray marching. We did actually use them because the ray marching solution is really quite slow. You really don't want to be having to test for intersections or solutions using the ray marching method for literally every ray that you're casting into your scene. So we did implement them back then, but I said at the time that it was something I would talk about later, which we're now doing. So the QB Ray logo that you're familiar with is made using ray marching, and as you can see here, each of these objects, the R, the A and the Y, as you can see here, all have their bounding boxes, which are shown here, and we can see that the bounding boxes cover the volume of those particular shapes completely, okay, like this. But what exactly does the bounding box do? Well, if we consider the bounding box here just for the letter Y, let's consider a hypothetical ray cast from our camera towards that letter. Okay, now of course in this case the ray is coming from slightly below the camera so that it's visible, but I think you see what I mean. At the point where this ray strikes the bounding box, okay, so we test for intersection with the bounding box first, we then cast another ray from that point of intersection, carrying on in the same direction as the original ray, and we test then if that ray intersects with the letter Y. Okay. Now, obviously, what we're going to do for any rays that we cast into our scene that don't intersect with the bounding box, we're not going to bother testing for intersections with the letter Y, or indeed any other shape that's enclosed in a bounding box. And you can see how that is immediately going to lead to a boost in an improvement in performance. In the case where we strike the bounding box and then we carry on and we don't strike the letter Y as we go through the bounding box, well, then we just carry on. The ray goes through the bounding box and out the other side, and then we carry on looking for intersections as normal. Okay, so that is the basic theory of bounding boxes. And we're going to look about how we implement those. Obviously, they're actually pretty simple. It's not really that difficult. The other thing that I want to talk about is composite shapes. So if you remember from the test scene I did for, I think it was episode 21. So if you remember the test scene that I did for episode 21, where we had the model spray can of QB spray, quantitative spray, I think I called it. And that's all very well and good. So we have an example of it here. Now, if we want to rotate this model, if we rotate it about its main axis, which in this case is the z-axis, no problem. We just rotate the three individual shapes that this object is made of, and as you can see, everything works fine. But what if we wanted to rotate the whole object, the whole spray can model, around a different axis? Well, if we rotate it about the y-axis, well, then we can see this is what happens, and obviously that's not what we want. Now, the reason it looks like this, of course, is because every one of these objects has its own coordinate system, and we're rotating each object individually about its own coordinate system rather than rotating everything as a whole. Now, we could do some complex mathematics and we could calculate exactly where each one would go so that we rotate them about their specific origins, and we could, in that way, create a spray can object that we could rotate, but that would be really complicated. What we want to do instead is have a way that we can combine the three shapes together into a single shape. And we are going to implement a new class, which I've called Composite Base, that allows us to do exactly that. And the advantage of doing that is that every individual object that we add into that composite shape still retains its own local geometric transforms, but the composite shape itself has its own geometric transform, and that allows us to define transforms that then affect everything. And you'll see what I mean when I come to do the code for that. Another illustration of this is this example here, where we have this ball orbiting around its own local coordinate system. So the ball has its own coordinate system, and we're rotating that about the origin. Now we could essentially parent that to a composite shape, which then gives us this arrangement here, and now we can rotate the composite shape. Now in this case, the ball is still rotating exactly as before. The code that makes the ball rotate hasn't changed at all, but we're rotating the composite shape to which the ball has been added. If you're familiar with Blender, this is the same as parenting an object to an empty. Essentially, the composite shape has no form of its own. It is essentially an empty, and you can use it as a parent for other shapes so that its transform then goes on to affect those. And indeed, we could go further with this example in that we can parent this composite shape to another composite shape, as you can see here, and then we can apply a separate rotation to that. So now we've got the three rotations going on simultaneously, which you can see results in really quite a complicated path. If we were to manipulate the ball just on its own and try to create the transforms necessary to duplicate this path directly, you can see how that would be really quite complicated. But doing this as a nested hierarchy of composite shapes actually really makes it quite straightforward. Okay, so that's what we're going to be talking about today. We're going to look at the code that we need to implement to make bounding boxes work, and then we're going to look at the specific class for the composite shapes, and I'll just show how to use it and how to use it to more effectively create a model of the spray can example. Okay, so let's dive in and let's have a look at it. Okay, so the first place that we're going to look is in the code for the box primitive shape class that we've created before. So first of all, looking at box.hpp, we have, as before, we have the definition here. Now, one thing that I have done actually that I should talk about is I've added this, which thanks to someone very kindly pointed this out over on the GitHub repository, as it's a much better way of passing pointers back to the specific shape. So we'll talk about it in a moment. So if we are now also inheriting from std enable shared from this, specified with the template of qbrt : box for the specific box shape. That's not to do with bounding boxes, but it is a change that I've made to the code, which we will talk about another time. So what I have done, and what the change that I've made that I want to talk about today, is that we have added a new version of the test intersection function that is specific for the box class. So the generic test intersection function that we have, as you know, accepts as input the ray, which we're testing for intersections with, and then it returns the data in the hit data data structure, and we override that for each primitive class from the object-based class that we inherited from here. Okay. What we're going to do, though, is create a unique version specifically for bounding boxes, because there are certain optimizations that we can do for bounding boxes that will make it faster to test for those intersections, because we don't need, for example, to know which face of the bounding box we've intersected with. We only need to know that we've intersected with a face. It doesn't matter which one it is. So that's one way that we can change that. So what we're going to do is overload the test intersection for the specific bounding box case. So we have this extra definition here in box.hpp. Okay. Okay, so looking at box.cpp for how we actually go about implementing that, we go down. This is the original test intersection function, which we talked about before when we covered the boxes, box primitive class. And here we have the new version, okay? And it's very, very similar. Obviously, it only accepts as input array because it doesn't need to return anything. It only needs to return a true or false Boolean to indicate whether there was an intersection or not. All of this code is exactly the same as we had before. Okay, so I won't talk about that. You can go back and look at the episode on boxes if you want to know more about that. And the difference is here, in the case of the bounding box, we're only interested in whether or not there was a valid intersection. We don't need to know which face was actually involved. Okay, so we simply loop over I from 1 to 6, 0 to 6, 0 to 5, in fact, because of course we have 6 faces and we have a valid intersection flag which is initially set to false. And this is the test that we need to do for a valid intersection, because we've already calculated our values of t, u and v up here for all of the faces, okay, that might have an intersection. And if that test is passed, then we set valid intersection to true, and then that will cause us to break out of the loop and we'll stop and we return the value of a valid intersection. Obviously, if we don't have any valid intersection remains false and we return false. And that's it. If we look back at the original code for testing for intersections, it's here. And this is a little bit different because it will calculate which is the smallest non-negative value of t. So not only find the valid intersections, but find the one that is closest to the point of origin of the ray, be that the camera or whatever. And then if we had a valid intersection, we went on to calculate the normal and do all these extra things. Okay, so you can see how the bounding box version is going to be faster because we're simply disregarding everything that we simply don't need. Okay, that's basically it for the changes. Now you will notice there is additional code here in the constructor, which I'm going to talk about in a moment, because there is one additional thing to talk about for bounding boxes. What we've done there is cover the basics of how we actually implement a bounding box using the box primitive class. But what we haven't talked about is how do we actually make that work. One of the problems is that we could define a bounding box for every shape, and we could have the user specify what the parameters of that box would be in terms of its position, its size, and so on. But that's going to get really cumbersome if you're trying to do a lot of modeling, if you're making quite a complex scene. What would be a lot smarter is if we could calculate the bounding box directly, automatically. And we can do that, but we have to know what the extents are, the maximum extents of every object are, okay? Now, another point to mention is there's no point creating bounding boxes really for the primitive shapes, because the tests for intersections for those are fairly fast. It's only really when we start grouping objects together or doing more complicated things such as ray marching, or if we go on to implement other ways of solving for more complex quadric or quartic surfaces or something like that. That's really where a bounding box really comes into its own. So what we are going to do is define a bounding box transform for all of the primitive shapes, not specifically a bounding box, and they can be used to calculate the extent. So let's just have a look at how we're going to do that. Okay, so looking at our object base class, initially the header file, so this is objectbase.hpp, we can see what I've done is added a bunch of new functions here. So we have two new functions here called getExtents, which are designed to be overridden, so they're declared as virtual. And there are two versions depending on what you want to pass in. One of them accepts as input 3 vectors, indicating the x limits, the y limits, and the z limits. And those are actually going to be the return variables, okay, because they're not declared const or anything like that. So getExtents, when you call it, will simply return the x limits, the y limits, and the z limits that define the maximum extents of this specific shape. We have another version that's exactly the same, except it accepts as input a parent transform matrix. Okay, now we're not really going to use that at the moment, but it is, needless to say, quite useful. And we have another function here called constructCube that simply accepts as input the minimum and maximum x, y, and z coordinates that define a cube. It could be a unit cube or whatever you want, and it returns the corners of that cube in an STD vector of QB vector objects. Okay, and that is everything that we need to change here for the header file, except down here we also now give every object that inherits from object base, so that's going to be every object in our scene, now gets a QBRT::GT forms. This is a geometric transform class that we created called m_bounding box transform, and we set a double variable here, m bounding box padding to 0. Okay, so all objects are going to get those and have access to those. Okay, so let's have a look at what this getExtents function actually does. Okay, so here we are. This is object-base.cpp. So let's have a look. We scroll down. So getExtents, this is defined in the base class, so we don't need to worry about actually writing this code in every one of our classes that derive from this, which is very useful. So first of all, this is the first version that simply has the 3 variables which we're going to output. It's of type void. The first thing we do is we use our construct cube function to construct a unit cube. Okay, so let's just have a quick look at construct cube. That's here. This is really very simple. Simply construct an array of the corner points of a unit cube, and that's literally all it does. We set this STD vector up of cubey vector objects called corner points. It has 8 corners. There are 8 corners to a cube, and then we simply define each one based on x min, y min, z min, x max, y max, and z max, and the m bounding box padding variable. Okay, now there's probably some cool way you could do this using a loop or loops, you know, but I mean it's only 8 lines of code anyway. It's not that long, and I think for readability this way is actually much easier. And that simply then returns corner points. That is it for construct cube. So if we go back, now, here we go. So we constructed our cube, we put our corner points into there. This is simply a unit cube, okay, from -1 to 1 in all 3 axes. And what we do is we then create a combined transform variable, which is an instance of the GT form transform matrix. And we get that by multiplying M transform matrix by the bounding box transform. Now we said that every object is now going to have a bounding box transform. And of course, we know every object has a transform matrix already. That's what specifies where it is and what size it will be and so on. And we're going to multiply those together to create a combined transform. And simply what we do is we then loop over all of the corners, and we're simply going to apply that transform to each corner in turn. Okay, the combined transform is applied to each corner in turn, and then we compare the position of that corner point to our minimum and maximum x, y, and z coordinates, which start out at these values and then get modified as we go through that loop. And you can see that what's going to happen is that is going to define the maximum extents in space that this particular object occupies. Okay, if we look at this animation here, we can actually see more clearly what's going on. So here we have a sphere, and you can see around it the hollow box marked by these small spheres and cylinders marks the extents that are calculated using this method for that sphere. Now the reason we multiplied the bounding box transform by the transform matrix is because we want this the extents of the shape to change. So if, for example, we modify the transform matrix to distort our sphere, as you can see here, we see that the shape of the extent varies accordingly. So as we scale the sphere in different axes, we can see how the extents vary. And indeed, if we rotate it as well, we can see that the extents vary, so that they always cover the bounds in space, the spatial bounds of that shape. Okay? Yeah. Okay, so let's have a look at how we actually would go about implementing this for a couple of the different primitive shapes, and then that should be enough of an example to see how that's going to go on, and you know how we do the same. I'm not going to show the code for literally every one, but it'll show enough to show how it should be done. Okay, so if we look at the sphere class, so this is object_sphere.cpp, what we can see is in the constructor, so one thing I have done here is define the default UV mapping for every shape, but that's just from the UV projection from the last episode. I just realised it would be quite nice to define a default, which can go in the constructor for every primitive. But now what we also do is we construct the default bounding box, and this is what defines the extent. So we set the M bounding box transform using the set transform function from that class, and in the case of a unit sphere, obviously we are centered on the origin, we don't have any rotation, and we maintain our unit size, so we simply set our scaling to 1, 1, 1. Okay, so that gives us the default bounding box for the sphere, and this is the transform that is multiplied by the transform matrix for the object that created the animation that we just saw. Okay, let's have a look at a different example. Okay, so if we look at object_plane.cpp, Now we can see here exactly the same. We set the default UV mapping that's now done for all of the primitives, but we set the M bounding box transform exactly the same way. So we have no translation, we're centered at the origin, we have no rotation, of course. So the default plane, remember, is a unit plane that is lying in the XY axes, the XY plane, okay, arranged vertically. So we want we want sort of a unit bounding box X and Y, but it doesn't need to be very high because the plane is, of course, infinitely thin. So we set the scaling to 1 in X and 1 in Y, and then 0.01 in Z, okay? And it's exactly the same for all the other primitive shapes. We simply define the default M bounding box transform to make sure that we would fit the original shape in its original coordinate system before any other transforms are applied. Okay, that's basically it for the code that I've created to implement bounding boxes. And actually what we've done so far is only really talk about implementing a bounding box transform to define the extents of all of the primitives. We haven't actually implemented any bounding boxes yet because, as I said, putting bounding boxes around the primitive shapes is not particularly useful because the intersection tests for those are quite fast anyway. Where they do come in useful is when we want to start grouping objects together, which of course we're going to do for the composite base class that I talked about at the beginning, that will allow us to create or more easily model different shapes. So let's have a look at that now. Okay, so two new files for Composite Base that go into the QB primitives folders, compositebase.hpp. Okay, so this is the definition of the class. Everything here is pretty standard, except that it has its own namespace called shapes. We define our class, Composite Base, which inherits from object base, of course. We have our constructor, we have our destructor that we have to override from the base class. And now we have a function to add subshape, which accepts as input a shared PTR of type object base to a subshape. Now this is the function that you call to add shapes to the composite class. You define all of the subshapes exactly the way we've been defining shapes so far. Except now we will create an instance of Composite Base. We'll see how this works in a moment, and we'll use the add subshape function from the Composite Base class to add those shapes into the Composite Base. Now, Composite Base has its own version of the getExtents function, so we're going to override that from the base class. Other shapes don't need to do that, but for Composite Base we need to calculate the extent slightly differently, so we will do that. We also override the test intersection method. And then we have a function to update bounds, which is if you modify any of the subshapes after creating the composite base, you need a function, some way to update the extents. Okay, so we have update bounds that will do that. We have a private function called test intersections. Okay, and this is actually what does the intersection testing for all of the subshapes. So we have just this one function that is called with array really to test for intersections, and then that is going to call test intersections, the internal private function. Accordingly, we'll talk about that in a moment. We have the actual bounding box, so we implement that. It's called m_bounding box. It is an instance of qbrt : box. We have a flag to say whether or not we want to use it. That's true, obviously. We have a vector for our list of subshapes, so a vector of shared PTRs to instances of object base, and then we define our object limits, which are what we return from getExtents. m_xlim, m_ylim, and m_zlim are both two-dimensional vectors, like so. Okay, let's have a look at the CPP file for this. Okay, so compositebase.cpp. In the constructor, we are going to define the initial values for the limits, and these start at xmin. We set its initial value to 1 million, and xmax its initial value to -1 million. Okay, we do the same for ylim and zlim. The destructor, we don't need any code there, that's easy. So this is now the function to add a subshape, okay, which is accepting as input a shared PTR to an instance of object base, okay, called subshape. And what we're going to do is we're going to modify the extents of this composite shape to accommodate the new subshape, okay? So we set up 3 new variables called xlim, ylim, and zlim, which are QB vectors of type double, each are 2-dimensional. And then we call the getExtents function from the subshape, passing to it those 3 variables. So that will give us the extents of that subshape. So that is why we did the work that we've just been talking about to worry about defining the extents for all of the primitive shapes. When you add a shape into the composite shape using add subshape, it will extract the extents using the code that we've just been talking about. And then very simply, if the new xlim minimum is less than the existing xlim minimum, then we modify the existing xlim minimum, and so on. That's a really standard code. We do that for xlim min, xlim max, ylim min, ylim max, and zlim min and zlim max. Okay. And then we're going to modify the composite shape bounding box to fit those new extents. So the thing we have to do is determine the size. So the x size is going to be the maximum x limit minus the minimum x limit, and the same for y size and z size, of course. We define the center points, which are simply going to be the minimum x limit plus half the x size, and the same for y and the same for z. And now we've got everything we need to actually update the bounding box transform. So just as we did for the primitive shapes, we now do bounding box transform dot set transform, except we have our center point here. Okay, we don't have any rotations, we're not worrying about those for bounding boxes, and we have our size, which is x size divided by 2, y size divided by 2, and z size divided by 2. Okay, and we also modify the bounding box. Now that's important because in this shape we have actually defined a bounding box. We're not just defining the bounding box transform, so we need to do bounding box dot set transform matrix to m_bounding box transform, and that takes care of that. And then finally we push the subshape back into our mShapelist variable using mShapelist.pushback subshape, and that's it. It's pretty straightforward. We have a function to update the bounds if any of the subshapes should be modified. So of course this is storing pointers to the subshapes, not copies of the shapes, right? So you can modify the shapes freely after including them into a composite shape if you want to. And in the case that you do that, you would call the update bounds function just to make sure that everything's changed. And this resets xlim, ylim, and zlim to 1 million and minus a million, and so on, exactly as we've seen before. It loops through all of the shapes in shapelist using for auto shape in mShapelist. Okay, pretty cool C++ syntax. I always like that. And just as before, we get the extents of each shape and we modify mxlim and mylim and mzlim accordingly. Okay, and then we modify the bounding box and the bounding box transform just as before. Okay, so that's pretty straightforward. We modify the getExtents function. So we've talked about this from object-based, and we're overriding that because we need to do something a little bit differently. In the case of this, we're going to construct a cube based on the limits. So we construct a cube from xlim min to xlim max, ylim min to ylim max, and zlim min to zlim max. Okay, and we're going to apply the transforms to that cube and then compute the limits. So we set these to the large values initially, and then we apply m-transform matrix to each of the corner points. Okay, and then we calculate the new limits accordingly, and we simply set those back into those variables that are then output from here. Okay, so you can see how that's different from the version of getExtents that we had for the primitive shapes, where we simply applied the bounding box transform and then the transform matrix here. We simply create the cube here, okay, and then we are simply then applying the m transform matrix in the forward direction to get the new extents. We also have to override the test intersection method because obviously this is no longer a single shape. So test intersection has the same format of all the test intersection methods, except as input the ray and the hit data structure that we're going to put the results into. We first of all test if this object is visible. If it's defined as not visible, there's no point doing anything, so we just return false. We copy the ray and apply the backwards transform. Okay, so m-transform matrix.apply cast ray, and we store that into bck ray. And then we're going to check for intersections with our bounding box. Okay, so if the bounding box use bounding box flag is set, or we have an intersection. Yeah, so if we're if we're not using the bounding box, of course, then we test for intersections all the time. So if not bounding box, or if m-bounding box or test intersection bck ray returns true, then we will go on to test for intersections with our sub shapes. Okay, so if we don't intersect with the bounding box and m use bounding box is true, then we don't test for intersections. Okay. Notice we're using the new version of the test intersection function. So bounding box is an instance of qbrt : box. And so we only pass the ray. We don't get any output except the Boolean return value, true or false. Okay. So assuming we did intersect with the bounding box, we now have to check for intersections with all of our sub-shapes, okay? And we define a world intersection point as a three-dimensional cubic vector. We define an initial distance, current dist as 100 million, and we create temp hit data instance of our data structure. And we're going to call the test intersections method, passing to it the ray, the original cast ray, the transformed ray, the world intersection point variable here, current dist, and temp hit data, okay? If that returns a value that's greater than -1, then we know we've intersected with a subshape, and then we do our normal things in order to return the results. So we calculate the new normal, which we get from M transform matrix at apply norm, okay, to temp hit data dot normal. So this is going to contain, temp hit data here will contain the hit data from the subshape that we have intersected with, okay. We normalize that, and we use the compute UV function from the object that we hit here in order to calculate our UV coordinates for the particular local point of intersection, and we store the UV coordinates in m_UV coords. When we come to look at multi-threading later on, we're going to have to modify this because this is definitely not a thread-safe way of doing things. I am aware of that, and we will deal with that later. Okay, and then we simply return those values into the hit data data structure. We return world in point into hit data.py, new normal into hit data.normal, temp hit data.color into hit data.color, and so on. I don't need to read through all of those. And we return the pointer to the object, the subshape that we hit. And that's the important thing with the composite base class. What it's going to do is it returns a pointer to this individual subshape that we had an intersection with. There's no point simply returning a pointer to the composite shape itself because it's an empty, it has no form. There's no intersection with it specifically. There's only an intersection with a subshape, which of course could be another composite shape, okay? So anyway, and then we return true because we had an intersection, and in these other conditions we return false because we didn't. So the test intersections function, this is quite simple. All it's going to do is loop through all of the shapes, check if they're visible. If they are visible, it calls a test intersection function for each one using the original format. Okay, so it's going to generate hit data that we've defined here, and that will return the results of that intersection. If shape test is true, then we transform the intersection point back into world coordinates. We compute the distance. If this is the closest intersection, then we modify everything to that. If not, we carry on through the loop, and in that way we end up returning just the parameters of the intersection that we encountered first within of all of the shapes within our composite class. Okay, so hopefully, I know I've rattled through that quite quickly, and I hope it wasn't too confusing, but hopefully you can see that what this allows us to do is to group objects together. So the composite class, composite base class on its own has no form, it has no geometry, but it does have its own geometric transform matrix. And then you add subshapes into it and it creates a group which are contained within a bounding box that is automatically calculated. Okay, now that's really important. So when you then, if you create a bunch of subshapes, add them to a composite base, all you've got to do, the only object you have to put into the scene is the composite base instance, okay, that contains the subshapes, and it handles the subshapes automatically itself. And the cool thing about that is that if you cast a ray into the scene and it doesn't intersect with the bounding box for the composite, for the group of objects within the composite base, then there's no intersections performed with any of those primitive shapes in that composite class, which is much, much more efficient. Okay, I think if you think about that, maybe I'm not explaining it as clearly as I could, but if you think about it, hopefully that will make sense. What I want to do now is just look at a quick example. So this animation shows what's happening to the bounding boxes to the extents of the composite class. So looking back where we had our sphere and we had defined this cube around it corresponding to the extents, if we now can put that sphere into a composite class, and into a composite base class, and we're going to add a second sphere. We can now move the second sphere, okay, it's still within the composite class, and you can see how the extents of the composite class, shown here in purple, vary as we move that second sphere. And if we now go through and apply the same range of transforms to the first sphere that we did originally, you can see how the extents of the composite shape vary to always exactly accommodate the combination of the subshapes. No matter what we do to the subshapes, the extents of the composite shape will always match. Okay, and that's the powerful thing. So it will always create a bounding box that exactly contains the geometry within it, which is really what helps to make everything so efficient. Okay, so let's have a look at how we would actually use this in a scene. Okay, so looking at the scene e21.cpp file that we talked about in episode 21, the last episode, what I want to do, let's just come down to where we define the three shapes that create the spray can. Okay, so the uncommented code here, this is the original, we define spray x and spray y so that we could vary the position of our can, and then we create the body, which is a cylinder, we create the cone for the top, and we create another cylinder for the actual top itself. Okay. Okay, so what we have here in commented out code, that's commented out at the moment, but this is the code we would use to use the composite base class. Okay, so we create an instance of composite base, the new class that we just talked about called spray can. We can set its tag if we want to, set its visible flag, and then we use the add subshape function to simply add spray body, spray top cone, and spray top into the spray can instance, okay, into the composite base class. So that is these three subshapes here. Okay, and then we set its own transform matrix, and we can define its position, its rotation, and its scale. It's commented out at the moment because I want to show examples with and without it. Okay, and then we have the rest of the scene is defined as normal. If we're going to use it, we simply push back spray can into our object list, okay, as it is. So nothing else there has changed. Now with all of that commented out, let's just render this and let's have a look at the result. Okay, so here I am at my command line. So I'm just going to run QBRay now. So this is the version with all of that commented out. Bring that over so we can see what's happening. It's very slow. I'm going to cut the video to make it a bit faster. Okay, and there we go. So that's the result that we've seen before. We have the spray can here. This is the object of particular interest. So let's close that. Now let's go back to the code. Let's put in the commented out code and we'll see how it's different. Okay, so the first thing I'm going to do, let's just comment out those and put in those. We'll set the position to 0 because we're going to take care of that now in the composite base class, right? I'm going to include this code that defines spray can as an instance of the new composite base class. And down here, what I'm going to do is comment out the code like so, that we don't need to worry about pushing back the individual shapes anymore. Now we just need to put spray can into the scene and it will take care of everything. So let's save that. Let's go to the terminal window, compile, and let's check that we get the same result that we had before. Okay, so back at the terminal window, run make, let's just compile that, like so, and run /QBRay. Okay, let that run. I'll speed this up as before. Okay, and there we go. So the first thing to notice, that looks pretty much exactly the same, and it's faster. Notice to 68 seconds now instead of 75. So the reason for that is, of course, that we put these three shapes in a bounding box. So when we're testing for intersections over here, or over here, or over here, we don't need to worry about testing for intersections with those. So that has made everything faster. And you can see that obviously if we were to divide the scene up further with bounding boxes, we could probably reduce the runtime further. Now there is one thing to note that's wrong about this, and I wonder if you've spotted it, and that is you see the reflection. Okay, so although our textures and colors have rendered normally here, the reflection is just black. Okay, and when I first did this, it took me ages to figure out why that was, and the problem actually comes in the material base class, and it's a minor error that I've made in how the reflection colors have been calculated. So let's close this. Let's go and have a look at material base and let's see how to fix that. Okay, so here we are, material-based.cpp. Luckily, it's quite an easy fix. What we do is we come down to here where we calculate compute reflection color, okay? And what we have is, at the moment, we are testing whether closest object has a material. Now the thing is we changed everything to use the hit data structure, and what I haven't done is modified this since. And it works for all shapes except the new composite shapes. And the reason is, of course, closest object, which comes from here, closest object comes from this cast ray function. That is going to contain a pointer to the composite shape, which is an empty. As we know, it has no geometry of its own, so of course it doesn't have a material, which means that this code is never going to get called. What we want is to interrogate the subshape that caused the intersection to see whether it has a material, and of course we can do that because we wrote the composite base class to return a pointer to the subshape rather than to itself. So what we need to do is comment that line out, put that line in, and we are going to, here we go, comment out this version of the code for that and put this version in instead, like so. And we can do the same here. This is the original version here. No, actually it's not. We're already using the new version there, so that's fine. Okay, everything else is fine. That's the only changes that we need to make. So let's save that. Let's go back to our terminal, compile, and fingers crossed, we should see the correct reflections. Okay, back at the terminal window, let's just compile those changes and let's run QBRay again. As before, I will shorten this sequence. And there we go. That has, as you can see, fixed the problem with the reflections now. Now, that doesn't really demonstrate, I mean, that's exactly the scene that we had when we started. It renders a little bit faster. It's a bit slower now than it was before, still faster than the original, but you'll notice it has gotten slower because it has to calculate the correct reflections. It's not a particularly exciting demonstration. One thing I want to do, let's just show that we can now rotate this as a whole object without having to worry about what happens to the individual subshapes. So let's go back to the code for the scene class and have a look. Okay, so I'm back in the scene class here. Now, we have defined our spray can object and it has its own transform. So just to show that, I'm going to rotate about the y-axis by -m pi divided by 4. So let's save that. So we've modified it. We've got the translation that we had before, and we now have a rotation about the y-axis by -m pi by 4. Let's compile that and see what we get. Okay, back at the terminal window, run make. Okay, and as we run QBRay, again, I will shorten this sequence. And there we go. So we can see that's the result. We see that we have now, by specifying only a single transform, we've rotated all of the objects. And that's really the power of using something like the composite base class, because it really allows us to create really complex geometry, and then we can manipulate it and everything really quite easily. This is a very simple example with just 3 subshapes, but you can see that once combined together, we can transform them whatever using just a single transform matrix. Now, it doesn't take much imagination, the way that we've to think about the power of this, because the way that we created the composite base class, we can put composite base instances into composite base instances. So the subshape could be another composite base instance. And using that, we can create really very complex geometries relatively easily. And we've also seen, of course, with this demonstration, the bounding boxes, this went from 85 seconds to 75 seconds, okay, for this example. But it's a much more complicated example. So, you know, we've made 10 seconds of improvement to our rendering time simply by putting a bounding box around this shape. And okay, and that really shows the power of bounding boxes and reducing the number of intersection tests that you have to do in terms of ray tracing performance. That is the #1 way, really, of making ray tracing go faster. Now, this ray tracer QBRay, as it stands, is very slow. Okay, it shouldn't take anything like 75 seconds to render that scene, you know, and there's quite a lot that we can do to improve the performance of this, which is something that I want to go on to look at in the next episode and maybe next couple of episodes. We'll see how that works out. My private version, as I showed in the previous video announcing what was coming up this year in 2023, I showed the difference really of how much faster my private version is. So there's an awful lot we can do to make this run faster. Making a fast ray tracer was never my objective. Really, QB-Ray is for educational purposes, just to understand how all the different techniques work, rather than necessarily being high performance. But even so, you know, there's still a lot that we can do to make it faster than it is. Anyway, that's everything that I wanted to talk about today. I really hope that's been of interest. If you like this video, please do remember to hit that like button. And if you haven't subscribed to my channel already, then, well, please consider doing so that you don't have to miss any future videos. Thank you very much. And yeah, just leaves me to say thank you very much for watching. I really enjoyed making this video. I really hope you've enjoyed watching it. And yeah, I really look forward to seeing you in the next one. Thank you very much for watching. Bye.